Okay, so all along we've been saying statistics has got three main components, and we spoke about the first one, variability. We spoke about the third one, probability, and now we talk about the main point of all of this whole course, and that is inference. So today we start talking about inference, and this is when the magic starts happening. First, let's define it. What do we mean by statistical inference? Here's a definition that we can use for this course. We can say that inference is the use of inductive methods to reason about the distribution of a population. So we're interested in a population and its distribution. How does cholesterol level vary within this population? But we're not going to measure the whole population. We're going to base our inference on the basis of knowledge obtained in a sample from that population. So a sample is just a subset of that population. So there we have definition of statistical inference that we'll be using. So schematically, what we've got is we've got this population out there. This is the focus of our interest. This is what we really would love to measure. We'd love to go out there and measure everybody in this population, and then we've got it all set up. But we cannot do that. For whatever reason, we cannot do that. So what do? We take a sample from this population. Then, on the basis of the sample, we are going to make inference about the population. So that's our challenge in this module. Now, let's look at these components one by one. First of all, we've got the population. So what is a population? Well, it can be real. So it could be everybody you know, everybody in your town, everybody in your province, in your state, in your nation, whatever. A group of people. It can be real, like that, or it can be conceptual. It could be everybody in the future who's going to have cancer and how we're going to treat them. Or it could be even more conceptual. It could be, well, what would happen if we treated everybody with this treatment? No, let's think about what if we treated everybody with this other treatment. So you can't have both, of course. So you can only, these are conceptual exercises that we can do, and this will help us in making our decisions about the future health policies that we might wish to implement. So it can be real, it can be conceptual, it can be past, it can be current, it can be future, it can be the past. What happened in 1917, 1918 flu epidemic? It can be current, or it can be future, as I said, all future patients who will have diabetes, all future patients who will have cancer. Now, this sort of makes sense. The more homogeneous it is, the easier it is going to be for us to describe. The more variable the population, the more difficult it's going to be for us to describe it, or measure it, especially if we're going to base this on a sample from this population. So for example, if we're all 4 feet tall, then that would be very easy to describe, and a sample of size 1 will tell us how tall we all are if there's no variability. So the more homogeneous it is, the easier it is to describe. Now, what we're going to do henceforth is we are going to try an exercise. So you've seen the Framingham Heart Study data, all 4,434 patients. Now, you've got that data set. Let's consider them as our population. Okay? So in our exercise, we're going to do that. So for example, here are the first 7 measures. Here's a summary of the first 7 measures we've got on our population. So for example, death is 0.349, that's about 35%. So about 35% of the 4,434 died. Angina, we have 16% roughly experienced angina. Total cholesterol, the average was about 237. Now here we've only got 4,382 measurements. We'll ignore that fact that there are some missings, but they average out, for the ones we have, they average out at about 237 and a standard deviation of about 44.6. And the systolic blood pressure, etc. So here we have these 7 measures. We've got many more, as you know, of course, but here are just the first 7. Okay, so that's our population. We're going to treat them as a population. Now, we're going to take a sample from this population. If we want to make inference about the population as a whole on the basis of this little sample, then what would we want from our sample? We'd want our sample to be representative of the population. So if our population is 50% male, 50% female, we don't want a sample that's all male or all female if sex is important in the thing that we're measuring about our population. So the sample must be representative. Now, think about this logically a little bit. How do we know that the sample is representative? See, I mentioned one measure, sex, should be 50-50 in the sample. Okay, now what about age? Well, we should have the same distribution of age in the sample as we have in the population. Then what about BMI? Well, we need the same distribution. It's impossible to be truly representative if we literally mean that we have to have the same distribution on every single measure we can imagine. It's impossible to do, number one. Number two, how would we know? The only way we would know is if we actually knew the population. In which case, why are we measuring it? Why are we even taking a sample? So the answer to this question is, must be representative. Question mark, if you want to put a question mark there. The answer is, we don't know. We never know if it's truly representative, typically. Okay, so what can we say about this? Well, what we use is we use this random device. We're going to take a random sample. What that means is everybody in the population has an equal chance of being in the sample. So we're going to take a random sample. Why? Because theory tells us that on average, we will have a representative sample. So on average, things are going to cancel out so that we have a balance. Okay? So suppose, let's try with our new population. Suppose we take a sample of size 49 from our population. Okay? What we can do is we can use Stata to help us do this. Now, Stata has a random device. It's not truly random. It's called a pseudo-random number generator. And what you can do with a pseudo-random number generator is give it a seed. Now, the manual suggests that possibly choose a random number. And one idea is take out a dollar bill and look at the number on the dollar bill. So on my dollar bill, it says G72576466A. And that's this, I took off the front G and the back A, and that's the seed that you see up here. So that's the dollar, that's this dollar bill. Okay? Now, so I set that seed. The advantage of setting a seed is that whenever I set the seed, then it sets the thing to start at that value, so subsequently we get the same values. We can't predict what they're going to be, so that's where the random idea comes in, but they get reproduced. That's the pseudo part. And that's good for science because we like reproducibility in science. But anyway, so then you say sample 49 and count. The reason why you put the comma count is that if I hadn't put that there, I would get 49% of the population in my sample. But this says I want to have 49 observations. And here we go. So looking back at those 7 variables again, we've got 49 deaths And remember, this was at about 35. It's now at 33. So within our sample of 49, we've got 33% deaths. The angina is 16%, and so on. The mean of the total cholesterol level is 233, and so on. So if we compare our population of 4,434 to our sample of 49, we see that, as we said, the deaths was 35% in the population. In the sample, it's 33%. Close, not bad, but fine. The ranges, so for example, total cholesterol level is from 107 to 696. The range in the sample, of course, has to be smaller. That's why we're forever breaking records in sports, etc. Look at the total cholesterol level. Let me put these side by side so that we can so it's easier to make a comparison. So here we have 35% versus 33%, 16% versus 16%. So we're close there. Actually, we couldn't have been much closer. 236, 233, and so on. So the means are pretty close. Here's 182 versus 79. So not bad. Actually, we should not forget about the standard deviations. The standard deviations in the sample are also pretty close. So in the population, the standard deviation of the total cholesterol level was 44.65. Here it's 42.74, say. 22 versus 22. So the standard deviations aren't bad either until we get down to the glucose level where we don't have a good value. It's only half. So the sample standard deviation is half the population deviation. But you can see why it makes sense that we can use this sample to make inference about the population. It's a sample of size 49. Turns out that that's a pretty big sample. In fact, the bigger the sample, the better our inference. We'll quantify this a little bit more closely later, but for now, here it is. What I did is I set the seed the same as before. Now this time I asked for a sample of size 10. And because I did this, we shouldn't do this, but I did this on purpose so that these 10 are actually the first 10 that went into making up the 49 in the previous sample. So here are the values. And once again, let me display them in such a way that we can do our comparisons. And so here is the population, deaths 35%. The first sample of 49 was 0.326. This one is 0.3. It's not as good. The angina 0.164, 0.163, 0.1. So that's not as good. Whereas this is better. So the mean total cholesterol level is better. That's the problem with randomized samples. We can't predict exactly how things are going to look. Now, I could have tried another set to make it, to cheat you into thinking, but that things are better. But I just, as I said, I used my dollar bill, and that's what we got. Now, on the other hand, the means might be better in the sample of size 10, but if you look at the standard deviations, the standard deviations are better estimated. The population standard deviation is better estimated by the sample of size 49 than it is by the sample of size 10. So the truth is 44.7. The 49 says 42.7, whereas the 10 said 72.5. And the same thing actually happens here with the systolic blood pressure. We're better off with the sample of size 10, but the standard deviation. So you can see in a number of places, actually here's the glucose level, where the sample of size 10 does better as far as the mean is concerned, and it does about the same thing as far as the standard deviation is concerned. So things are random, but we'll see in a moment that a sample of size 49 is better than a sample of size 10. Now, how big a sample do we need? That's the question. But what's amazing is that it doesn't matter what the population size is. Case in point, here are the results from Real Clear Politics of the last presidential election 4 years ago in the US, and the polls that were taken immediately before. So this would be like the last polls before the election. So here they are. The Marist poll was done the day before. So the election was in 1104. So it was the 4th of November. And here was the poll done just before that election. And the final results had President Obama getting 52.9% of the vote. And this Marist polls predicted that he would get 52%. McCain actually got 45.6%, and they predicted 43%. Okay, battleground. So all of these were done 1 day before, 1 or 2, 3 days, but up to 1 day before the election. Here are the averages. I'm sorry, here are the values that they predicted Obama would get on the basis of these polls, and the ones that McCain would get. Here are some that were quit like 2 days before, and these were 3 days before. So here are the various polls, a number of them. Now, what Real Clear Politics did is it takes an average of all those polls and came out with 52.1 for Obama and 44.5 for McCain. I don't think you can get much closer than that. And what's amazing about this is that close to 100 million people voted. 100 million voted. What were these polls based on? How many people? They didn't go and ask 100 million people. That was the whole election. They took a poll. They took a sample. What were the sample sizes? Well, here they are. The Marist poll was based on 804 LV's likely voters. The battleground was based on 800. This one based on 800. 3,000. I think that was the largest one. Yes, indeed. 1,200, 900, 971. On average, this is about 1,000. Each one of these guys, each one of these polls was based on about 1,000, sample of size 1,000. These 1,000 were predicting how, let's say, 100 million people were going to vote. Think about it. You can predict how 100 million people are going to act on the basis of 1,000 people. And look at the results. Okay? That's the magic. That's the magic I mentioned earlier. How can we do this? Okay? And this is the magic of random samples. So, we've looked at the population, we've looked at the sample, and now let's look at inference. So inference is from the sample, we want to infer about the whole. Okay? That's the inference. That's the magic. And we want to do it in a principled way. And so we have to deal with the uncertainty. We have to deal with uncertainty because we only see a small picture of the whole population. Okay? And we don't want to do like the Hindu parable of the blind men feeling the elephant, and depending upon what part of the elephant they were feeling they projected or they inferred about the rest of the elephant. Okay, so what we would like to do is handle this uncertainty by introducing probability so that we can measure the uncertainty. And that's the next part of our discussion.